and welcome to our Mars Innovation Forum session on environmental closed-loop life support systems. For those of you who don't know me, my name is Dr. Shauna Pandya. I'm a Canadian physician. Space medicine is my passion. And today we are here to delve into the world of ECLS, or closed-loop life support systems. And we have here with us today leading experts in the field. Our hope is by the end of this session, you will walk away with a sense of what our challenges are for life support systems for Mars, where we currently are at, where we're heading next, and how we can bring those benefits back to Earth. I'm going to go ahead and introduce our stellar panelists today, and then we're going to jump right into their opening statements. First off with us, we have Darren Semplatsky, the Associate Director of Business Development for Collins Aerospace. He holds with him 25 years of experience working on environmental control and life support systems. He has worked on key elements of life support, including for ISS and the commercial space sector, including critical items for oxygen generation, water production, and thermal control. Welcome, Darren.
Thank you.
Next up, we have Dr. Kavya Maniappu. She has an equally out-of-this-world background. She is a space scientist at NASA working in flight operations and training for EVA, or extravehicular activities, for the Artemis program, including spacewalks and spacesuits. She has also held a background in next generation CST-100 Starliner at Boeing, where she has worked on Starliner spacesuits as the lead, as well as flight test director for Starliner's flight tests. She has worked as mission evaluation room manager for the International Space Station and is an adjunct professor at the University of North Dakota, as well as an aerobatic pilot, scuba diver, and classical Indian dancer. Welcome, Dr. Kavya Maniappu. Next, we have Dr. Danielle Delat. She is an engineer with passions for human-computer interaction, space applications for machine learning, space systems, space and science outreach. Her background is incredible, bachelor's in aerospace engineering and with information technology from MIT, master's in space studies from the International Space University, PhD in aerospace engineering from the University of Tokyo, as well as having worked at NASA Goddard as an aerospace engineer on robotic satellite servicing. Dr. Danielle Delat, thank you for joining us today. And last but not least, we have with us Barry Finger, VP of Engineering and Chief Engineer from Paragon Space Development Corporation. As the VP of Engineering at Paragon, Mr. Finger has led technical leadership and balanced oversight of engineering development processes for the company. He holds a bachelor's as well as a master's in aerospace engineering from the University of Florida and is a 14-year veteran of Paragon. Mr. Finger and his engineering leadership team have maintained the technical excellence standards of the company's life support and thermal control products. So as you can see, if you weren't convinced before, we have exactly the right people to tell you all about getting us to Mars and the ecosystems that will take us there. So to kick things off, I'd like to invite each of our panelists to give us an opening statement specifically addressing, in your mind, what is the ideal ecosystem for Mars? Can we get to Mars with the ecosystems that we have today for ISS? And what are you working on in the world of ecosystems? So to kick us off, we're going to start with Darren, and then we'll move over to Kavya. Darren, please take the stage.
Thanks, Shauna. So for me, an ideal system would be a system that requires no maintenance, something that's easily repairable if there is some sort of issue. Autonomous operation, right? That's a big thing, right? So we don't have the same systems like we have on the ISS. These systems need to operate on their own without any intervention from the ground. And then, I'd like to see the use of common parts to reduce the overall spares, right? That's another big issue we're going to have going to Mars is, we can't bring everything with us. So if we use common parts amongst the systems, maybe that really reduces us in spares. And then finally, I'd like to see the system have the ability to utilize in situ resources, things like CO2, right? So Mars is 98% CO2. We could make things like oxygen with that. And then, we think there's water sources on Mars, and then, trying to figure out how to utilize that water with these systems. These systems are going to need to be really robust, right? So currently on ISS, our systems, for instance, like the air loop closure, we're around 42%. Right now on ISS, we're about 90% water loop closure, although that may be more with Barry's brine processor. And then we currently carry around 6 months of spare hardware on ISS. With Mars, there's going to be no resupply. So, NASA's recommending right now that we have about 75% air loop closure, get that up to 98% on the water loop closure, and then have a minimum of 3 years spares. So, like I said, autonomous operation, and then, no support from the ground is going to be key for these systems. As far as systems we've been working on, in support of a Mars mission, we have lots of things going on right now. So one of the systems we're testing on ISS is called the thermal amine scrubber. So this is a CO2 removal system. It was launched the International Space Station in August of 2019. We've currently had a few issues with it running, but right now it's up and running in 2-bed mode. We've had pretty good luck with that. Some other systems that we're currently getting ready to work on is the advanced oxygen generation assembly. So this is an O2 generator. We're trying to incorporate that 15 years of lessons learned. We're trying to make that more maintainable. Right now, it has a lot of really heavy ORUs. So some of those are around 300 pounds. Obviously, that's not something we want to have to take on a mission to Mars. That system should fly sometime in 2024. Another system that we're working on for closed loop life support is a Sabatier 2.0. We originally flew the Sabatier in 2010, so this was a flight experiment designed for 5 years of operation on ISS. We actually had to take that back a couple of years ago, bring it back down to the ground. We had some issues with the CO2 contamination. It destroyed our reactor, so the system shut down. We brought that back. So we have several upgrades that have been identified by us and NASA that we're going to incorporate. We just finalized a contract on that, and that system should fly in 2024. Another area we've been working on is the water processor. Although we haven't had a lot of issues with the water processor over the last 10 years, it is one of the critical systems for closed loop life support. So right now we have an issue with the CAT reactor. We've had water leaks. So we developed a lower temperature, lower pressure catalyst for that. We've upgraded the seals, and we're getting ready to fly that. I'm sorry, we flew it earlier this year, and we're getting ready to test that over the next several months. So we have some other systems. We can talk about those later in the thing. So I'm going to turn it back to Shauna.
Thank you so much for that wonderful overview, Darren. Now we're going to hop on over to Dr. Kavya from NASA to tell us about what you are working on in EGLIS and how you see us heading to Mars with current and future systems. Go ahead.
Thanks a lot, Shauna, and it's really wonderful to be sharing this panel with experts from the field. I really echo a lot of what Darren has mentioned, and having a closed loop life support system for Mars will be very, very crucial. And if we can get to 100% recycling of water and generation of oxygen, those are going to be our key technologies. A couple of things I would like to bring from my field of expertise. The first one being we're going to Mars, and which means we need to be thinking about new spacesuits to provide life support system for our astronauts while they go venture out doing science and mission objectives. That's going to be really key. And the current suits that we have on the International Space Station are specifically built for microgravity EVAs, extravehicular activities. And so as of now, as we all know, the Artemis program is up and running, and at NASA, we are actually building our next generation spacesuit called the XEMU, Extra Mobility Unit, which will be tested on the ISS for both microgravity, and then eventually we carry on that new design over to the lunar surface with more design upgrades to provide the dexterity, mobility, and the ability for the astronauts to get out and venture to do EVAs. And so thinking about Mars, we need to now think about, the additional gravity factor that we have there when you compare it to Moon. We are still looking at 38% gravity, and which means we need to think about making our suits a little bit more lighter, at the same time offering more capability from life support standpoint to go do an EVA for long durations. And that's going to be a key. And one of the other important aspects, which actually I did my PhD in, is dust mitigation. Whether that's Moon or Mars, we are on these planetary surfaces. It's going to be a key environmental challenge that we need to overcome. And right now, NASA is working on various different dust mitigation technologies to incorporate into our spacesuits, as well as how our ecosystem within the landers and our spacecrafts can ensure that these particulates don't make it into our cabin atmosphere. And that's going to be key for Mars as well. We are going to be there away for, it's a long duration mission. We cannot just, take up multiple spacesuits at the same time. So going back to what Darren said, maintainability, robustness is going to be key for these life support systems, whether that's internal ecosystems within the spacecraft or the habitat that's going to be put out on Mars surface, or the spacesuits itself. For me, I also have a background in flight crew operations and training. So wearing the crew hat, we want to maximize our crew time on mission and science objectives. So maintainability and the time it takes to maintain these ECLS systems should be optimized. So we're not spending too much time just cleaning our suits or trying to replace these modules. And so on-orbit repairability and being capable of replacing any of these ECLS modules should be much more easy to do and operate. And then finally, another aspect that falls within the ECLS system is incapacitated crew rescue. So think about a scenario that we have astronauts venturing out on Mars. Maybe they're getting samples, they're far away from their habitat, and we have an injured crew. Now, we need to think about how we are going to bring them back, but also have sufficient capability within the life support system of the suit, and the suit itself being designed to ensure that we bring the astronaut back into a pressurized module and provide necessary medical capability and operations there. So, and Sean, I'm sure you would, relate to that much more. So I think with the current technology we do have a long way to go, in the sense we are taking those steps, we're using ISS as a platform to test out our technologies. And the next step would be going to the Moon, which is much more closer than Mars, and testing out our technologies and taking that next step to using these next generation technologies for Mars.
Thank you so much for that fascinating overview of the challenges of EVA, where we're headed with XMU and testing, starting with Artemis and how that pertains to Mars. From one doctor to another, we are going to head on over to Dr. Danielle Delat. And she comes to us as a space systems engineer from Draper. Her background there is incredible. She's recently wrapped up leading Draper's display and controls subsystem for one of the entrants to NASA's Artemis human landing competition. And she is going to tell us her perspective on challenges for ECLS, for Mars, and how we're going to get there. Dr. Danielle, go ahead.
Thank you so much. And it is really wonderful to be here with everyone. So the ideal ecosystem is going to incorporate fault tolerance, reliability, and maintainability from the beginning. And caveat, when you said maintainability, I really felt that. So I completely agree with you. The ISS is a great jumping off point, but ultimately that is an open loop environmental control and life support system. And I think you would agree here. We can add water, ammonia, food, or any new parts we need almost anytime. And when it's really great to have that place to test the new technology in microgravity, especially over a long period of time. But the risk is so much lower. When you go to Mars, the stakes are just so much higher. A crew member who becomes incapacitated is just could completely tank the whole mission. Whereas on the ISS, you have a lot more redundancy built in. So the systems we build for Mars have to have that redundancy from the beginning, and we have to think through all of the different ways that you could have cascading failures down the road. So on the Human Landing System project that just wrapped up, Draper's work included the displays and controls for the Dynetics lander, and this, of course, included Eclipse displays. So we were balancing heritage designs that would be familiar to the crew, and innovation, all while tailoring to the specific Eclipse system for the vehicle. My team also got to collaborate with colleagues at Draper and folks at partner companies to develop fault-tolerant computers and avionics architecture for the whole vehicle. So fault tolerance, in case anyone isn't familiar with that phrase, it can be in different levels. So you might hear someone say something like, a system is 1 fault tolerant or 2 fault tolerant. And whatever that number is the number of errors that can be survived without losing the mission. So if a system is too fault tolerant to mission critical, you can have 2 different failures. So this can take a lot of forms, but out in space, a good example is computers. So computers are susceptible to bit flips due to radiation, and if a bit flips in the wrong place, that can cause all manner of havoc on your system. Imagine something getting stuck in an on position that needs to be off. So fault tolerance can be at the component and the system level, not just the bit flips. Say your power supply goes down in one system. If your power supply goes down, it doesn't matter if you have 2 redundant devices if they're hooked up to that same power supply. So that can be really frightening, but by designing the system from the beginning and thinking through all of the cascading impacts, it is possible to design fault tolerant and reliable systems. And talking about some other exciting developments. So I don't personally work on this right now, but I found out about this and I really wanted to share. So Draper's biotechnology area has some really cool things with great potential, I think, for Mars Eclipse. One of our heritage systems is the air quality monitor, which has been working for over 20 years on the ISS. And follow-on technology was rolled into something called the differential mobility spectrometry device, which is actually being used in Earth-based medicine and is being considered for use on submarines. And to target everyone's favorite, radiation risks, I guess I get to be the first person to say radiation on this panel, we have to think about what happens if a crew member gets cancer in transit. So something promising there, and this is far in the future, but we're not going to Mars tomorrow. We have some time. Draper has actually partnered with Kite Pharmaceuticals to develop bioprocessing technology that takes a person's own white blood cells and turns them into cancer-fighting machines. So right now, this is expensive. The whole process takes a few weeks, but the vision is to make this device smaller and get the system into clinical trials in a small number of years. So this project is focused on the Earth version now, but the drive to make that system small and portable makes it a potentially life-saving device for a space mission. So that's something I'm really excited about. And we're going to need lots of ideas like this to make the Mars ecosystem. So I'm so excited to be here with this great panel.
Thank you so much for that wonderful overview. My mind's going a mile a minute, thinking of all the challenges. Some of these are frightening, but some of the promise of what's being worked on is just fascinating. So to take us home with this introductory overview, I am going to bring Barry up. And Barry, I know you have some visuals, so take it away. Give us your several-minute intro to challenges and current state of the art for Eclipse for Mars. Go ahead.
Yeah, and this is just a background on Paragon, but I really can answer your questions because a lot of it is kind of covered in this chart. You asked about what do we want in an ideal Eclipse? What is that? And a lot of these words have already been said: robust, resilient, distributed. Maybe that hasn't been talked about as much. You want that functionality spread throughout the habitat or the spacecraft. You can't just have everything in one location. And we'll get more into this. Another thing you asked about was, can we go to Mars today with the current ISS Eclipse? Well, if you're talking about the basic fundamental core technologies, I'd say yes, we can do that. There's some good work there. Darren talked about systems that they have running on that Collins has provided on ISS. It's hard to imagine leapfrog changes in some of those core technologies. But will we get there with the existing implementation of those? No, we won't. Again, this has been talked about here already. The systems that are on ISS are designed very differently. They're designed for maintenance, regular maintenance, replacement. line replaceable units or ORUs at a much higher level than you would do on a mission to Mars, where the mass you have to get cargo there is very limited. So from that perspective, just as we kind of get into this with the existing technologies, you can't get there with the implementation that ECLSS has done now on ISS. And then the third thing you asked about was, what are we working on? And that's why I'll just use this chart to talk about what we, Paragon, are working on right now in life support. We're doing things like integrated ECLSS solutions for current space programs. We do the life support system for the Northrop Grumman HALO vehicle. That'll be the first habitat to orbit the moon. And Dream Shapes, we do things like build radiators. And these don't sound sexy or exciting, but these are examples of products that have to work day in, day out in these extreme environments. And in the case of the Mars habitats, where they're not going to be thrown away and probably reused, that they've got to have long life in those environments. Darren talked about ISS and water recycling. We do a brine processor. That's direct to NASA, and that closes that water loop. That's one of the critical, if you're going to do regenerative life support, I think we'll talk about that a little bit more. That's water you got to close. It's what we all use on a daily basis more than any other input to our bodies. And you've got to get that percentage up there quite a bit. Otherwise, you have to go do ISRU. And that's the last item over on the right. Paragon right now is really pushing forward. We have several contracts where we're doing basically the purification. NASA has developed a whole process train to go from raw water to all the way to propellant or purified water in between for crew consumption. And so we're working on developing technologies specifically to purify that water to where you can then electrolyze it or split it into hydrogen and oxygen. And so that's kind of a range of what we're doing. And just because I'm a little bit different, if you go to the next slide, I always like to do these, when I do these panels, I look at what's on the website and what we're asked to talk about. And I think we can talk about some of these things. There's like 4 things I think that said this conference was about: defining challenges, sustainability. And these are things that get beyond like what we're talking about in ECLSS, but they're important because we all have to play a role in addressing these, either as a citizen or in the companies we work for. So commitment, we've got to make sure that at society level and corporations in the United States and the international, we're ready to go, we're willing to go do this. Another thing I hope we can talk about more, it's a little technical, is be willing to fail safely along the way. We have to learn by doing. We can't compromise safety for the crew, but we can get there faster by learning and being able and allowing ourselves to fail. And recruiting new communities, I just say, like, there's an example, there's this new space out there, maybe Paragon's part of that a little bit, although we're in our 28th year, but that's part of like tactically getting these new communities. And Wade, if you go to the last slide, this is just, again, 2 other things you had: create strategies to solve these challenges. And I say that's essential because all this takes money and time and effort. And as a society, that's energy, the investment that's taken away from other things. So we have to show that what we're doing is worth it to society at large. And that comes down to actually go do what we want to go do here. We have to find a way to fund this over decades. Not a single mission has often been done, or a single vehicle campaign, if you will. And then you did ask about terrestrial markets. I think that's part of it. I listed some things there: carbon capture, indoor air quality, water quality, and sustainable agriculture. Those are things that when we really push the envelope in life support, that can come back, and we have contracts in other parts for government contracts where we look at some of these things now.
Thank you so much for that fantastic overview. So many considerations here. Some of it seems daunting. Some of it seems science fiction coming to reality. So Dr. Danielle, your biotechnology overview of white blood cells that can help mitigate the cancer risk induced by radiation, that's that's next generation stuff. That's science fiction come to life. So of all of these myriad challenges, I want to ask the panel, what scares you? What keeps you up at night? So why don't we start with Dr. Danielle, and then we'll go over to Dr. Kavya and Barry, then Darren. Take it away.
One of the things that I would say keeps me up at night is there's concern that the crew may not be physically capable of doing the landing on Mars when they arrive. And as someone who cares about guidance, navigation, and control and the computers, that's a really big deal. if that were the case, that would essentially mean that you would have to have an autonomous landing and plan for that to be your primary mission, which is not a popular thought among astronauts. When we were thinking about the lunar landings, the astronauts were telling us constantly, we want it to be able to land this ourselves. It's great that you're building in this autonomous capability, but we want to be able to have it if anything goes wrong. And for all of the Apollo missions, there was the capability, but the vehicle never landed by itself. So I'd say that the crew not being functional, and some estimates say that it might even take 2 to 3 days for the crew to be functional in gravity again when they reach the surface. So that's a really big deal. But that assumes microgravity transit, and I'm sure that there are lots of people thinking about how to make the crew as healthy and strong as possible when they get there.
Thank you so much for that. Dr. Kavya, what keeps you up at night in the world of ECLSS? What scares you?
Yeah, so I'll still stick to my areas of expertise here. So when I think about it, and when I was actually doing my research, I didn't realize how crucial and actually bad moon dust was. And we were on the moon during the Apollo missions for no more than 3 days, and a total of 22 hours of EVA. And we actually ended up almost puncturing a suit on the last Apollo mission. And astronauts complained about, various impacts of dust on operations, on suits, on hardware. We were not too far away from puncturing a pressure bladder. And being in a suit, that's your only life support system when you're outside the spacecraft or the lander. And if we don't think about trying to mitigate this and add dust mitigation control into our suits and the ECLSS system that has to work through contamination control once the astronauts come inside, I think that's going to be a really big challenge for us. And as we all know, spaceflight is hard, but human spaceflight is really hard. And so if we don't think about things now and try to start incorporating these into the design, I think it's going to be way more expensive. And when we go to the moon or to Mars, we want to go there with all systems working, and we are there to do science. We want to study and meet all of our mission objectives and science objectives. So what good would it do that we go there and we don't have our equipment running as we should just after a couple of EVAs? And you might really relate to this also, Shauna, that going back to the Apollo mission, dust actually caused some health problems as well, and more exposure to dust on the moon, for example, and now even on Mars. When we think about Mars, it's going to cause a lot of health issues, and we need to protect our astronauts from a life support system standpoint from that exposure. So both spacesuits and their habitat, their cabin atmosphere, we need to make sure that we are providing appropriate contamination control systems to help mitigate that.
That is so true. It really struck home with me, when one of the astrophysicians called my attention to the biomedical lessons from Apollo. And, you really realize it's not just clogging up suit joints, it's skin irritation, it's respiratory irritation. So absolutely, that's something that would keep me up at night as well. Darren, what keeps you up at night in the world of ECLSS?
So there's a couple of things that keep me up at night. One, we're going to be operating for long periods of time without resupply, so that scares me. And then the other thing is, we're most likely going to pre-position a lot of this hardware, so these systems could be sitting for up to years at a time. So one of the things we worry about is long periods of dormancy, right? Things like water likes to move around into areas you don't want it. Bugs start to grow in areas you don't want them to grow. So I'm just worried when we go to turn on some of these systems, they may not operate as planned. So yeah, I think we really need to take a long, hard look at, how we're going to pre-position this hardware, and then, what are we going to do about things like dormancy and the effects that, sitting for long periods of time can have on this hardware.
Yeah, that makes perfect sense. And I want you to hold on to that thought, because we're going to get into that a bit deeper in the next question. So we will explore that a bit more. But Barry, I want to turn it over to you. Tell us your ECLSS nightmare.
So yeah, my nightmare is been in a lot of sci-fi movies, but it's an atmospheric leakage. I mean, again, so there's two parts to this. One is that's not necessarily equalist in a way. And its recognition is, again, as we develop this system level solution, where you go put your energy and how you smartly design your system, and that you have multiple airlocks and you have multiple unique volumes where the crew can fail gracefully and retreat to. And that's one part of it. Because the other reality is like we've been talking, you're going to have limited resources, even if you're doing ISRU, to go overcome an emergency cabin depress. If you're getting, all of your oxygen from Mars CO2, it's going to take time to go. We really have a whole, vehicle's worth of O2. So that puts pressure on the equalist to then be sized very large to be designed for these non-nominal events. Another thing I think is important and I think we've been talking about it, but designing for maintainability, and this kind of goes against something that was said earlier by another one of the panelists, but we do have, that crew is going to be there. Humans are the most innovative, resourceful computers that we have, that have arms and limbs and can do all types of things. And I believe the systems that we put out initially, the robotic systems for ISRU and getting ready and mining the atmosphere and such, those will be pretty well engineered and resistant to the environment. But as those crew members start going in and out, and the humans, the biology associated with humans, and that dust moving in and out, we've got to do maintainability a little bit different. And then one last thing is kind of related, but I've seen this sometimes. We all are familiar with the technology that's all around us as part of our lives, our cars, our phones. That's all well and good, but like Darren said, there's not going to be an iPhone store down the road when that phone goes out. So we have to inject high tech and computer and automation at the right level. We can't, I use the example, at ISS, you can't turn on the lights without a computer. So we just got to be smart about where we put automation in.
So that is, all of this is enough, to make us pause and think. And so one question I want to get into has kind of been alluded to in most of your answers, and Darren had touched on it a bit more, is, what about the shelf life? Like what happens, when we leave these systems sitting idle? And so the question is, when we look at current ECLSS capabilities, how does the longevity need to change, or does it? And then as part of that, when we look at the length of resupply and how much we anticipate that it will change with current technologies, months, 6 to 9 months on the way to Mars, how are we planning to increase the both duration and longevity of an ECLSS system on Mars and decrease the need for resupply? So that's a lot. Pick your favorite part of that question. Darren, we'll start with you.
Yeah, so the current systems we developed for like the ISS, so they all had a 10-year design life, or the majority of them had a 10-year design life. And so, certainly enough time to go on a mission to Mars, right? But a lot of those systems, even though they were designed for 10 years, they required periodic maintenance, replacement of parts, and then, we had systems that just didn't operate as planned. So, no matter what we do, we're really going to have to figure out how to get these systems put together and get them tested long before we go on a mission to Mars. Like I said, a lot of these systems require, some care and feeding, and I think Barry was touching on this a little bit. Humans like to figure out things and work with them. So I think overall the systems will have enough design life and enough shelf life. It's really just making sure that we test them out long before we ever venture out on a mission to Mars.
Perfect. Okay, so then here are some of my other questions. When we let's get it back into the world of high tech that we were just talking about. What are the greatest technical leaps that we need to make, or what technologies would you like to see emerge to help us survive and thrive on Mars? Kavya, we'll start with you.
So I want to bring in a little bit of a personal insight here, and actually with everything that's going on with COVID as well, and relate the high tech to how we can bring this technology back to Earth. So I would start with water recycling. As both Barry and Darren had mentioned, I think closing the loop on water will be very important for Mars exploration. But when I think about this particular aspect and how it can help our societies here on Earth. I think about countries in Africa and how we might be able to help those people and communities there with such technologies. Similarly, with all of the COVID going on in the last few weeks in India, where I actually was born there and I have some extended family there, we've read news about how they lacked medical oxygen and there was not enough supply. And when I think about that and how our technologies and the high-tech technologies from Mars could help us, I think closing the loop on oxygen and being able to generate it in situ will be important on Mars, but then we can bring it back to Earth in situations like what we're facing right now. So for me, water closure, the O2 generation and regeneration, and then finally contamination control will also become an important aspect if you're going to Mars, and then eventually bring those technologies back to Earth.
Thanks for that. Who else has ideas of technologies that would make your lives and jobs much easier for solving ECLS challenges on Mars? Who wants to go next?
I can kind of hit on that one a little bit. So for me, I'll say something again. I hate to be always controversial. I hope I'm not that way. But it's not just these fancy technologies, right? We are getting better and better at transporting mass, and it's still going to be a challenge to get enough mass there. But having sources of consumables, the stuff of life, oxygen, water, those foodstuffs, that's really important. And again, we have to do this smartly, especially if we're talking about the early missions. If we put all of our eggs in one basket of this regenerative system that's going to just be magical and hit that 98% all the time, man, we're going to make it really hard on ourselves. So I think that's one of the things we have to look at, is getting that right balance between fully regenerative, highly regenerative, and then that living off the land. And that's one of the things, whether you're talking about Mars or the moon, we're really looking at technologies that can allow us to get those resources in that local environment.
Thank you so much for that. And I do want to expand the question to an important aspect that Kavya had mentioned, is that it's not just Mars that's going to benefit from all of these technological advances. We have challenges. We have no shortage of challenges when it comes to surviving and thriving on Earth. So in addition to advances that'll help us on Mars, what else can we do for Earth? So keeping that in mind, Darren, let's go to you and then to Danielle.
Yeah, so I think a lot of these systems have applications back on Earth, like the oxygen generation, the water cleanup. We build a Sabatier, basically pull CO2 out. So there's some of this stuff could be, I'll say, more industrialized and brought back to Earth. And the money that we spend developing these systems, always seems to come back and benefit what we currently do here on Earth. Some of the other things I was thinking about when you were asking about new technologies, and there's a lot of things out there right now, like in-space manufacturing that we're starting to work on, and coming up with ways to build things simpler in space. I think that'll eventually help back here on Earth as well. And then things like intelligent systems. How do we make these systems smarter? AI. There's a lot of things right now that are going on, and these technologies are changing day to day that will help us all as a world in the future. And then lastly, things like red hard electronics, even though not a lot of applications here on Earth, but there has been a lot of I'll say advancement in that field over the last several years that for a mission to Mars, I think it's going to be critical. And trying to get those technologies infused into everyday life, I think will continue to grow things here on Earth, as well as helping us on a mission to Mars.
Thank you so much. And Danielle, take us home on this topic. What technologies and what applications for Earth are at the front of your mind?
Well, space is an extreme environment. So figuring out how to make something work in space translates to all sorts of extreme environments on Earth. We care a lot about the mass of something, the size, how long it can last. So if we make really great products for space, that can help us on Earth. And actually, a specific example is follow-on technology from the air quality monitor that's up on the ISS is actually being used right now in a trial at Brigham Women's Hospital to detect fungal infection. So previously, apparently, this detection took days, maybe 5 days, and this device can detect it in 30 minutes. So I think that's a really cool example of how technology made for space can help us here on Earth. But there's so many of those. Actually, NASA, JAXA, ESA, all of them publish the spin-off guides every year about cool technology from space that we're using on Earth.
Absolutely. So in the final 2-3 minutes that we have left with Earbuds, I know that the audience must be burning with questions, and we want to give them time to pick your excellent brains. Just give us a sense of what our hope for the future should look like. How far away are we from developing the systems we want to see? Or how close are we? Let's do a quick rapid fire, starting with Danielle and then Kavya, Barry, Darren. Go ahead.
I think we're as close as the political will and funding are.
Very diplomatic response. Kavya, over to you.
I actually echo exactly what Daniel said. I think we're as close as what funding levels we get, and the commitment, like Barry mentioned, it's the commitment, and not just commitment for, that cycles through every 4 years, but a long duration commitment to make long duration space exploration to Mars possible.
Yeah, I echo that. I think a lot of it has to do with the funding that we get, but we have technologies today that we could use to go on a mission to Mars. I think we just got to really start on that path to get there. Will we be there by 2033? When that's next period when they'll be the closest. I don't know, but it's something we should certainly strive for, and I think it is achievable if we can get the funding to do it.
Perfect. And Barry, take us home.
Yeah, just absolutely. We can definitely do it by 2033. Everyone said it. We have the technology. We can go do this. We gotta have a mechanism, a pathway, an infrastructure, something that allows it to happen. But we're not waiting. That's what everyone should know. We're not waiting for some magic technology to be invented to allow us to go do this.
So there you have it. From the mouths of experts, it is unanimous. If you're a policymaker or investor who is out there, make it happen. Invest in Mars technologies, not just for human exploration of space, but for bringing good back to Earth. It's on you. There's your challenge. So thank you so much for the audience for joining us today. Thank you to all of our panelists, Danielle, Kavya, Darren, Barry. I know that we are seeing audience questions roll in. So without further ado, let us have the audience put you on the hot seat and ask away.